speaker today, we will speak about yet more APO about Norway. So then I will learn to play. And maybe I have to notice that we are celebrating beyond 50 years of quantum field theory, also Relativistic reports. And his last tour de force was joined with Steve Summers, so maybe his talk is also particularly interesting.
Okay, well, thank you, Laszlo. And I'd also like to thank the organizers for giving me the opportunity to speak at this celebration of the achievements of algebraic quantum field theory over the past 50 years. Perhaps I should say a little something about this title. Shortly after I placed a paper in the archive carrying this title, I received an email from a retired physicist where he asked me, well, what's so remarkable about the vacuum state? It's just a vector in Fock space. So I hope there's not many of you who share that view, but in any case, I certainly hope that by the end of this talk, you'll certainly not share that view. So actually the notion of vacuum has got an amazingly rich history in the history of human thought, and it has been viewed in every conceivable way, from an exemplar of the Godhead to the worst heresy generated by the devil. Now, in modern science, however, what the vacuum is roughly speaking that which is left over after you remove everything which can possibly be removed, whereby possibly means physically possible, not logically possible or technically possible. And therefore, the vacuum is just an idealization. I shouldn't say just. It's an idealization which is only approximated in the laboratory and in nature. But it is a very rich and useful concept. Now, by this time in this conference, it's not really necessary to speak about the formulation of algebraic quantum field theory, but I would like to re-emphasize something that Professor Haag said the other day. His original motivation was to try to set up a formalism within which physically significant quantities are derived from those things which are operationally given in the lab. The question is, it's a conceptual question, and I think it's an important conceptual question. How much can in fact be derived directly from these things that are given operationally in the laboratory, and how much is one simply forced to posit in order to come up with a meaningful theory? And in my view, what AQFT has demonstrated time and time and again is that the answer ultimately is going to be you can derive almost everything from the operationally given quantities. All the rest can be avoided. You don't need all of these additional things. They can actually be derived. You don't have to posit anything. So I'd like to remind you that the observables that we talk about in AQFT, which generate the local algebras, these are in principle determined by measuring devices in the laboratory. There are actually certain equivalence classes of measuring devices, and the states are also certain equivalence classes of preparation devices. So at least in principle, the basic data of AQFT are determined operationally. And I think, by the way, that that's the strength of algebraic quantum field theory, that because we're so close to the operational sources of the science, we can formulate in a mathematically rigorous way conceptual questions that cannot be so formulated in other approaches to quantum field theory. So in any case, as you know, we begin with an isotonous net of unital C-star algebras generated by all the observables measurable in the space-time regions O. I'm only going to be talking about Minkowski space today. And to begin with, I'll be talking about D space-time dimensional Minkowski space. And then the other ingredient is a state or certain states on the quasi-local observable algebra generated by the net. Now, once you have a state on this quasi-local C-star algebra, you can go to the GNS representation associated to that state, and there you can look at the von Neumann algebra generated by the representatives of the local algebras. I'll denote those by R omega of O, and the von Neumann algebra generated by the representative of the quasi-local algebra. Now, under different sets of general conditions, it's known that these von Neumann algebras, these local von Neumann algebras, are mutually isomorphic for a large class of regions. So in other words, the algebras themselves do not carry very much physical information. The physical information which is carried in AQ of T is actually encoded in the inclusions of the algebras. Now, the standard definition in AQ of T of the vacuum state is the vacuum state is a translation invariant state on a covariant net, maybe Poincare covariant or just translation covariant, a covariant net whose corresponding GNS representation satisfies the spectrum condition. In other words, when you are in the GNS representation of this translationally invariant state, then of course there's a strongly continuous unitary representation of the translation group acting covariantly upon those von Neumann algebras R omega. The self-adjoint generators of that unitary group commute. They have a common spectrum, and that spectrum is required to be in the closed forward light cone. That's the spectrum condition, which is a stability condition for the theory. And the corresponding GNS representation is called a vacuum representation. Now, this is the standard definition, but I'd like to emphasize that there are crucial elements which are not expressed solely in terms of the operationally given quantities, the observables and the states, namely the action of the translation group on the space-time and on the observable algebras, and also the stability condition, this condition stated in terms of generators of this representation. These are not stated in terms of the observables. Indeed, even the Minkowski space on which we begin with this net and the translation group acting on that space, these are also at this point not stated in terms of, solely in terms of the observables and the states. I'll come back to that later. Now, in case some of you have come under the maleficent influence of a certain professor of economics at the University of Houston, I'd like to emphasize that the vacuum state does exist. You probably are not aware of this little controversy. You can ask me about it privately later. Concrete examples have been rigorously constructed of this structure by various means. These things exist. We're not talking about the empty set here. Moreover, general conditions are known under which to a quantum field model without a vacuum state can be, under certain conditions, uniquely, and also under certain conditions, physically equivalent, locally unitary equivalent. In any case, general conditions are known under which to a quantum field model without a vacuum state can be associated a vacuum state. In fact, these ideas go back to Borges, Haag, and Schroer. The idea is to consider the expectation in a state of a translated observable for suitable states and sufficiently many observables as a translation tends to space-like infinity. That was the original suggestion. Now, subsequently, the discovery of soliton states and of topological charges excluded the existence of such limits in general, but under certain circumstances, these limits do in fact define a vacuum state on the given net, even though it didn't have initially a vacuum state. So the mathematical existence of a vacuum state is also assured in many circumstances in representations without one. Now, let me just briefly mention these. Because some are a little bit involved, I'll only be able to indicate them with key words. So examples of such conditions which assure the existence of this associated vacuum state, the vector phi in that expectation. If it's in what Buchholz and Friedenhagen called a massive particle representation, then that works. In fact, it works maximally. You get a unique vacuum, and the associated vacuum representation is locally unitarily equivalent to the original one. Another condition, which is very recent, a strengthened nuclearity condition, which is satisfied by both the massless and the massive free field, implies that there's an associated vacuum state, and it's unique. And then there is this, which is not quite so complicated to express, so I thought I'd write it down. For a sufficiently large set of local observables, such that for some R, remember D is a space-time dimension, so strictly less than the spatial dimension of the Minkowski space. For a suitably large set of such local observables, this is finite, is finite for all phi in the representation space and all A in this suitably large set of local observables. And this is a kind of time-like asymptotic abelianness condition. So just wanted to mention these. They're not that widely known, I think. So this exists. We have plenty of examples of vacuum representations. Now, what are the properties of these vacuum representations, of these vacuum states? Well, one of the first things that was observed is the famous result of Ray and Schlieder, which was originally proven in the context of Weitman theory and was later proven in the context of AQFT by Araki. And that is that in any vacuum representation satisfying locality and this weak additivity condition, the implementing vector, the vacuum vector, if you will, is cyclic and separating for all of these local von Neumann algebras. Now, many of you youngsters learned that the second day in your lecture on quantum field theory, and have probably not thought much about the meaning, shall I say, the operational meaning of this. The fact is that when this theorem was proven and its significance began to sink in, it generated a great deal of controversy, which is, by the way, is not ended. There are still people writing in various journals about precisely the controversies which were engendered by the Ray-Schlieder theorem. Just as a brief indication, I can't get into the controversies, but as a brief indication of the source of these controversies, the cyclicity of the vacuum vector for any local algebra, no matter how small the localization region O is any vector state can be arbitrarily well approximated by a local perturbation of the vacuum state. And therefore, in principle, in a laboratory on Earth, in fact, in my bedroom closet, I could, by artfully manipulating vacuum fluctuations, construct a house on the backside of the moon. This is a consequence of the Ray-Schlieder theorem. Now, for the separating aspect, that the vacuum is separating for these local algebras, it has some important consequences. One is, among other things, that any non-zero local projection has to have non-zero vacuum expectation. That means, in particular, that there are no local particle counters. Because if C is a particle counter, then since there are no particles in the vacuum, its vacuum expectation must be zero. If it were local, it would have to be zero. Okay, so these are two of the sources of controversy which are still going on wildly outside of our little union. We don't worry about it too much, but other people do. Now, some other more recent properties of the vacuum which have been proven, since quantum information theory is such a fashion, I'd like to point out to you that we also have something to say about quantum information theory. So in particular, it's been proven that the vacuum is entangled across any pair of local algebras in a vacuum representation, as long as the two algebras are space-like separated. And it doesn't matter how far apart they're separated, the vacuum state is still entangled across them. Now, entanglement is the central resource in quantum information theory. In case you're not familiar with it, let me just briefly give you the definition at least. One says that a state is entangled across a pair of algebras if it is not a certain limit of a mixture of product states. And a product state across such a pair is a state so that this expectation factors as a product of these two expectations over all A1 in this region and all A2 in this region. So, not only is a vacuum entangled, but it's entangled no matter how far apart the regions are separated. So in principle, one could even use the vacuum as a resource for quantum information experiments. Now, more recently, a stronger result was proven that the vacuum is in fact one distillable across such algebras, and that means, roughly speaking, that at least in principle, you can, by purely local operations, distill or increase the entanglement to maximal entanglement. Now, along those lines, I'd like to mention also a result of this nature. In the vacuum state, Bell's inequalities are maximally violated across the any pair of local algebras whose regions are space-like separated but tangent. So that means that their closures intersect. Now, there are, in quantum information theory, many different quantitative ways of measuring entanglement of a state. They're not equivalent. But all of these different ways agree that if Bell's inequality is maximally violated, then one has maximal entanglement by all of these measures. And so a consequence is that the vacuum is in fact maximally entangled. It's a maximally entangled state. Okay, now in case you're not familiar with this, let me just briefly mention that Bell's inequality in the Clauser-Horn-Shimony-Holt version of the Bell inequality can be stated this way in the algebraic language, that 1/2 this expectation in this state phi of this funny combination of observables is bounded by 1 for all AI or A1, A2 in this region, all B1, B2 in this region with norm less than or equal to 1. And that means, therefore, that if you take the soup over the left-hand side, over all of these guys, you get 1. If you get 1, that means that you've got Bell's inequality satisfied. Bell's inequality is not violated. However, what was proven is that, in fact, for these spatially separated tangent regions, that supremum is not only greater than 1, it's equal to the square root of 2, which you can show is the maximal possible value that this quantity can reach in any theory that can be formulated in terms of C-star algebras. So that is maximal violation. Now, as interesting as these observations are, the fact is that every single one of the things that I've pointed out, all of these properties, are shared not only by the vacuum, but also by any vector which is analytic for the energy, which is interesting also in itself. But for the purposes of this talk, this begs the question, well, what then distinguishes the vacuum? So, my answer to that question involves the Tomita-Takasaki theory. What I view as the answer to that question, what I mean by that, what I view as the answer to that question involves the Tomita-Takasaki theory. Just in case there's somebody here who's not familiar with it, let me tell you that if you're given a von Neumann algebra with a cyclic and separating vector, namely precisely those two properties which the vacuum has with respect to any local algebra, if you have such an algebra with a cyclic and separating vector, then the modular theory of Tomita and Takasaki yields a unique, this is important, anti-unitary involution J and a positive, usually unbounded operator delta, both leaving the reference vector invariant and satisfying these additional conditions that the adjoint action of the modular involution on the algebra maps it into the commutant of the algebra. The commutant is all the bounded operators in the Hilbert space which commute with everything in M. And because this is a positive self-adjoint operator, you can, via the spectral theorem, define these unitaries. Those are called the modular unitaries, and the adjoint action of the modular unitaries upon M act as an automorphism group on M, the so-called modular automorphism group. Now, there's a great deal more structure which is involved here, and all of it is necessary in proving the results we'll be mentioning later on. But for us right now, the most important thing is the Ray-Schlieder theorem says that in a vacuum representation, one can look at the modular objects. They're uniquely determined for any local algebra and the vacuum. So pick the vacuum, it's now fixed. Let O change, and that gives us these modular objects as indexed by the regions in the space-time. Now, what is conceptually crucial, in my view, is that the modular objects are completely determined by the algebra and the state, in other words, by the observables and the preparation of the quantum system. Now, Gandalf has just shown us wedges, so I won't dwell on wedges, but I would like to emphasize some structure which he didn't talk about. He didn't need it. And that is, to each wedge, in fact, every pair of complementary wedges, there is associated an edge. And associated to that edge is a reflection about that edge. So for each wedge, there is this reflection through the edge of the wedge. And then for each wedge, there is uniquely associated a one-parameter group of boosts which leaves the wedge invariant. And at least in 4 dimensions, it's one-dimensional. That I represent by lambda W. One parameter subgroup of Lorentz boosts leaving the wedge W invariant. Okay, now, although the Tomita-Takasaki theory at first glance, certainly to those who are not familiar with it and familiar with its many accomplishments, because it has turned out to be absolutely crucial in the study of the structure of von Neumann algebras, but it's also, in my opinion, absolutely crucial to the study of quantum field theory. And the first indication that that was true was the Bisignano-Wickmann theorem. And I see Arthur has just arrived. Hi, Arthur. This paper was actually the first paper I ever read in algebraic quantum field theory when I was a graduate student at Harvard. Anyway, so Bisignano-Wickmann showed the following. If you have a net of von Neumann algebras locally associated in a natural way with a quantum field satisfying the Whiteman axioms, and therefore we're in a vacuum representation, then one has the following remarkable facts: that the modular involution associated with the right wedge and the vacuum vector is in fact equal to the product of the PCT operator associated with the quantum field and a rotation about pi, about the direction in which the wedge is opening up. So for WR, that's the one direction. And in addition, these modular unitaries exactly coincide with the, remember, a Whiteman field theory comes supplied with a representation of the identity component of the Poincare group. These modular unitaries actually coincide with the representatives of the Bruce group that leaves the wedge W invariant. Okay, so this was quite remarkable that these abstract objects have in fact this concrete geometric meaning. Now, a consequence of these, an immediate consequence of these, is that the adjoint action of the modular involutions associated with any wedge on any local algebra acts geometrically in this way, as does the modular group acting in this way. Now, let me point out a few consequences of these conclusions of the Wisignano-Wickman theorem. One is that if you look at the group generated by all of these modular involutions, they're all operators on this Hilbert space, you can multiply them together and make a group. We call this group the modular symmetry group. So if you look at this group, then given the conclusions of the Wisignano-Wickman theorem, then first of all, because this is true, you can see immediately, well, sorry, I guess you can't see it immediately. Forget it. It takes a little bit of work. But because these J's implement all possible reflections through all possible wedges, they actually generate the orthochronous Poincare group. And it follows that, in fact, the subgroup of J generated by products of even numbers of those J's coincides with the original representation of the identity component of the Poincare group. And in addition, that it supplies an extension of that representation to a representation of the orthochronous Poincare group, which also acts covariantly upon the net. So in other words, an important, for our purposes, for my purposes, an important lesson from this is, at least in that special case considered by Wisignano and Wickman, modular involutions encode the isometries of the spacetime. And also, remember, the translation group is the dynamics, encodes the dynamics of the theory. So then the translation group is in there, therefore the translation group is in there. The modular involutions encode the dynamics of the theory. Now, another consequence is that if the quantum field satisfies asymptotic completeness, so there are these asymptotic free in and out fields. So those free in and out fields are also perfectly good Whiteman fields, and you can look at their wedge algebras, and on the same vacuum state that was the vacuum for the interacting theory. So you look at the corresponding free modular involutions. Okay, then this product actually coincides with the S matrix of the theory. So these modular involutions encode the scattering theory as well. Another consequence, this time, of this result, and the fact that these Tomita-Takasaki unitaries have analytic properties which are directly connected with the KMS condition. A consequence of that is that the vacuum state is a thermal equilibrium state at this temperature in the observer's proper time where a is the acceleration of the observer, for every uniformly accelerated observer. Now, he's not going to burn himself, though, because at 1g acceleration, this is a temperature. But still, those of you who've heard about the en route temperature, this was the first mathematical justification of the existence of the en route temperature. The en route temperature was initially arrived at by a quasi-classical argument involving a linear detector, et cetera, et cetera. So this was a nice connection that was observed. And then another consequence of those relations that Bissignon and Wickman proved in their special case is this, that when you multiply these modular objects together, you get another modular object associated to a particular region. There is encoded in these products geometric information. But remember, how the algebras sit in each other also depends upon that algebraic information, and therefore algebraic relations among the modular objects are determined by and in turn encode information about the inclusions. And I remind you, it's the inclusions which encode all of the physical information in AQFT. So, algebraic relations among these modular objects encode that information. Okay, now, Bissignon-Wickman had this special situation, a net locally associated with a Whiteman field, and so we're in a vacuum state, and all this is true about the vacuum state. But are we in a situation that we were in the first list? Is this true for other states, or does it hold only for the vacuum state? In answering that question, I'm going to be answering another question. So let me talk also about this seemingly unrelated question. Recall that I emphasized that in the definition of the vacuum, the action of the translation group on the space-time and on the observable algebras, as well as the spectrum condition, are not expressed in terms of the operationally intrinsic states and observables. Is there an intrinsic characterization of the vacuum state? Okay, so it doesn't appear that these two questions have anything to do with each other. Now, just in case you're thinking to yourself, well, who cares if there's an intrinsic characterization of the vacuum state or not? I like the old definition, I'll just stick with it. Okay, so the role of the vacuum state in Minkowski space has proven to be so central that when theorists tried to formulate quantum field theory on curved spacetimes, they tried to find something that would replace the vacuum as a distinguished reference state. When they tried to do so, they ran into a number of significant conceptual mathematical problems. Now, I don't have the time to go through them, but let me just mention some representative problems. What could replace the large isometry group of Minkowski space in the definition of vacuum state in light of the fact that on a generic spacetime, the isometry group is trivial? And even in the situation where we have a very symmetric spacetime like de Sitter space, what could replace the spectrum condition, which is part of the definition of a vacuum state? What could replace the spectrum condition as a stability condition in such highly symmetric spacetimes like the de Sitter space where there is no translation? All right. Finding intrinsic characterizations of the vacuum state for Minkowski space have led to answers to these questions in other spacetimes. And I'm convinced that they will lead to others in the future. All right, so with that as a little bit of motivation, let's look at what we call the condition of geometric modular action. We have a state on a net. So this is a net. We're not assuming that it's local or has anything else going for it. It's simply a net. It satisfies isotony. We have a state on a net. We say that it satisfies the condition of geometric action if, first of all, the vector, the GNS vector associated with the state, is cyclic and separating for all the wedge algebras. That's so that we get these modular objects in the first place, so that we can start to work with them. And then, here's the teeth. if the modular conjugation corresponding to each wedge algebra and that state satisfies this relation, in other words, the adjoint action of that wedge involution on the set of all wedge algebras just leads you back into the set of wedge algebras. In other words, the adjoint action takes any wedge algebra into some other wedge algebra. Okay? Any wedge algebra, doesn't matter. Some other wedge algebra. Takes wedge algebras to wedge algebras. That's all that's required here. Now I'd like to point out that if we have the conclusions of Bissignano and Wickmann, then this property holds. Because remember, the adjoint action of JW is to implement a reflection about a wedge. And if you have any wedge reflected about the edge of any other wedge, you just get another wedge. So we're precisely in this situation. Okay, so it was shown that if you have a state on a net satisfying that condition of geometric modular action and some weak technical conditions which are not List, but which are all expressed solely in terms of the state and the net, then it turns out that the adjoint action of the wedge involutions is precisely that found by Bissignano and Wickmann in their special case. In addition, this modular symmetry group provides, as in their case, a canonical, strongly continuous anti-unitary representation of the proper Poincare group under which this net transforms covariantly. And this representation also leads omega invariant. Now remember, in the case of Bissignano and Wickmann, one had the representation already. One found that, in fact, the group J coincided with that representation. Here we have no representation. We have no action of the Poincare group on anything. That is derived, all right? Because under this circumstance, the modular involutions have this action. You can, in a canonical manner, construct out of the J's a strongly continuous anti-unitary representation of the Poincare group, which acts covariantly upon the net and leaves the vacuum, well, the reference vector invariant. In addition, the state satisfies locality. I mean, not the state, the net. The net satisfies locality. We didn't put it in by hand, we derived it. Okay, now in order to have a vacuum state, you need a little bit more. You need more than just a translation invariant state, which this is now. It's, of course, more than that. It's a Poincare invariant state. But you also want this stability condition, this spectrum condition to hold. So if, in addition, these modular unitaries are actually in this group. Now, this is a condition which does not refer at all to any space-time. This is simply an algebraic relation. These objects, completely determined by the operationally given data, are included in this object, which is itself completely determined by the operationally given data. So you check if that's true. If it's true, then modular covariance is satisfied. That is to say, this is true, and therefore this is true. And also the spectrum condition holds. So the state is actually a vacuum state. So this theorem answers both of those questions. A conclusion of this theorem is that only the vacuum state has the properties stated in the conclusion of the Bissignano-Wickmann theorem. And also this theorem provides an intrinsic characterization of the vacuum state. So from a suitable state and net of observable algebras on Minkowski space, one can derive a representation of the isometry group of the space-time, acting covariantly upon the observables, leaving the net, the vector invariant, et cetera, et cetera, et cetera. That's all very nice, but we started with a net on Minkowski space. The space-time itself and its isometries are not yet expressed in terms of the states and the observables. Can that be done? Okay, so can one derive space-time itself from a suitable state and collection of observable algebras? So the short answer is yes. I think I have time for the long answer, so let's get going. So, we no longer start with a net indexed by subsets of some space-time, because we don't know what space-time we're in. We just have a bunch of laboratories, and in these laboratories are clocks, and these clocks keep track of how long a certain experiment carried out in a certain spatial region is carried out. All right, so in other words, one just has this net of von Neumann algebras generated by the observables. The I are just elements of a partially ordered index set I, which you can think of as the set of all laboratories, because you can certainly decide if one laboratory is in another. And if one laboratory is in another, then certainly its set of observables is contained in the observables of the other. In other words, this net is given to you always. All right, now, if you've got a state on that net so that the corresponding GNS vector is cyclic and separating for these algebras so that you can get to the Tomita-Takasaki operators, the modular operators, then we've got this group J, this modular symmetry group generated by all of the involutions. It's now in our hand. And then you can look at that modular symmetry group generated by all of these involutions and check to see if the following is true. Is it true that when you act upon this net adjointly by all of these guys that you get back inside the net? So let's assume that the CGMA is satisfied. In other words, precisely the adjoint action leaves this set invariant. Then we look at the group J and we check to see what algebraic relations can be found in that group. All right, if certain, which I'm not going to list now, but if certain purely algebraic relations in J hold, then there exists a model of three-dimensional Minkowski space. I'll begin with that. There exists a model of three-dimensional Minkowski space. Now, the model itself is built on J. In other words, using these algebraic relations, we construct on J itself the necessary geometric structure so that it can be interpreted as three-dimensional Minkowski space. So there exists a model of three-dimensional Minkowski space on which each of these guys acts adjointly. So of course it can act adjointly on itself, on that group J, but it acts adjointly, now that it's been reinterpreted as three-dimensional Minkowski space, it acts adjointly as the reflection about the edge of some wedge. And the edge of every wedge is represented in this collection. All right, therefore, J is isomorphic to the orthogonal Poincare group, and once again forms a strongly continuous anti-unitary representation of the orthogonal Poincare group. But remember, that's great, but we can't talk about covariance yet because, remember, our net is not defined on this space. It's simply indexed abstractly, right? Okay, well, it turns out that you can also do the following. The same assumptions entail that there exists a bijection, an identification, a one-to-one correspondence between laboratories and wedges in your three-dimensional space, so that after defining the algebra observables associated to this wedge to be this original algebra, the resultant net of wedge algebras, we've now reinterpreted this original abstract net as a net of wedge algebras on this three-dimensional space. The resultant net is covariant under the action of this representation and also the theory, the algebras satisfy Haag duality. And if in addition this modular stability condition holds, then once again modular covariance is satisfied and the state is a vacuum state. So a net of observable algebras and a state determine under proper circumstances a space-time, a strongly continuous representation of the isometry group of the space-time, and an identification of each I with a suitable region of the space-time in such a way that the original net is now reinterpreted as a local Poincare covariant quantum field theory on the spacetime. Similar algebraic conditions in J have been found which entail that the resultant spacetime on which the reinterpreted observable algebras are then localized is four-dimensional Minkowski space, respectively three-dimensional de Sitter space. Now, let me just anticipate a question. A given structure, a given modular symmetry group can satisfy at most one of these sets of conditions. In other words, from the same state and net, you're not going to get two different spacetimes. You get one, at most one. Okay, so, and work is in progress on finding a suitable characterization of four-dimensional de Sitter space and also anti-de Sitter spacetime. Now, oh, thank God. We've got time to go through this list. I love this list. The modular involutions, JW, for the wedge algebras in the vacuum only, encode all of the following information. We're going to go through this list in a moment. Now, if some of these things, the green things, require not just what's going on with the J's, but also what's going on with the modular unitaries. So, in any case, though, it's the modular objects which are completely determined by the state and the observables. They encode the following information: the isometry group of the spacetime, a strongly continuous unitary representation of this isometry group, which acts covariantly on the net and leaves the vacuum invariant. It encodes the dynamics of the quantum systems. It encodes the scattering theory of the quantum systems. It encodes the locality, in other words, the Einstein causality of the quantum systems. It also encodes, and this I didn't have time to talk about, it encodes the spin statistics connection in the quantum systems. And then together with the modular unitaries, it encodes the stability of the quantum systems, the thermodynamic behavior of the quantum systems, and provides a characterization of the vacuum state itself. And then, as I mentioned, it even encodes the space-time itself. So, now, I went through a lot of results, and anybody who's interested in details and references, a convenient reference is this paper. You'll find more details and all the necessary references to get started looking at what I referred to. And with that, I'll end.
What is the source of the numbers 3 and 4 for the dimensions?
You mean in the algebraic relations? Or how do you mean?
Yes, you did not mention certain conditions. You need technical conditions.
That's right. Well, I mean, so the...
When do you get 3 and when do you get 4 dimensions?
Well, okay, so I suppressed the list of algebraic conditions for a good reason. Only in the case of the three-dimensional Minkowski space is the list short. There's actually six conditions in that case, yeah? Although we've worked hard to try to diminish the number of assumptions for the other spacetimes, and we've made some progress there, which is why it's taken so long for us to write these papers, because I didn't want to. But let me emphasize here, because I didn't do it this time, and I should have. This business about deriving the space-time, first of all, that is only going to work for very symmetric spacetimes, all right? Everything else on that list above that, however, can be expected to work also for spacetimes with low symmetry. In fact, we have concrete examples of that. All right. The other thing I wanted to make clear was this theorem where we have this list of algebraic conditions which tell you which space-time you're in, or you can interpret it as being in. We're not proposing this as some practical means of actually determining which space-time we're in, right? We're simply answering a conceptual question. Is it conceptually possible to, via the states and algebras alone? Okay, so the answer to that question is yes, for high symmetric spacetimes. But we're not trying to be, proposing, okay, why don't we go out and just check it for ourselves which spacetime we're in. That's not what we're doing, okay?
Can you get any dimension?
I believe so. Well, not, I can't get or one dimension, but above, I believe so, yeah. I haven't done it yet, though.
Could you mention that you have two different states of the same system of algebras, which give then rise to two different spacetimes?
I don't have an example for that, but that strikes me as conceivable. Yes. Actually, I might have it. No, wait. We have an example. We have an example. This transplantation paper provides an example. Can I say that? No, sorry. No, that's the other way. It's actually one state on two nets. Even though, all right, never mind. Sorry, strike that. But it's conceivable. Let me put it that way.
In the case of anti-de-Sitter, there is this one-to-one correspondence between wedges of anti-de-Sitter and double cones in the conformal bond.
Right, yeah.
Regarded as wedges in the conformal bond.
Right.
So in that case, one would not expect such a uniqueness, because from the point of view...
Uniqueness of what now? Uniqueness of what?
Well, that three-dimensional and four-dimensional cannot be true at the same time. In that case, just the collection of algebras and the modular data do not tell you the difference between four-dimensional anti-de-Sitter and three-dimensional conformal.
Well, we haven't looked at that in detail yet, but I think that there's going to be a subtlety that is being overlooked right now, and in your question. In other words, I don't accept the hypothesis, but it's certainly an interesting thing to look at carefully, and we're going to do that. Thank you.
Now, what is special about the quantum field? You produce the same, I imagine, if you have a net or Galilean variant. Yeah. So,
perhaps.
Why do you get the Poincaré group? Is that encoded in the special conditions you have?
Yes, because it's encoded. The conditions encode the space-time, and the space-time encodes the isometry group.
Yeah, would it work for Galilei?
Well, I'm not certain that has the necessary geometric structures that we need. We need what is called a hyperbolic metric space, and I'm not certain that. I mean, that's R4, but it's strange, right, geometrically? So I don't know. I'm sorry, I don't know.
Is it not the Borges relations for modular, for outside modular inclusions, which force the Poincaré group upon us?
Well, but you'll note there's nothing there. We're looking at the group J. We're not looking at the modular unitaries. All right, so the modular stability condition, which was that the modular unitaries are contained in the group J. All right, that entails, first of all, the modular covariance, and then because of the fact we've got this representation of the Poincaré group, that entails that Borcher's relations hold, and that's why the spectrum condition follows.
Theories, the ground state is typically not separating for local algebras, so even the starting point doesn't exist as long as a modular structure.
Ah, good then. I won't have to think about it. Thanks.
The last result here is not on an Abfeld set. Is an ordered set, so you have to
Well, it's not on the set. It's indexed by the set. It's indexed by the set.
adjust an index.
Yeah, it's just an index.
So it's not the net. So
No. I mean, it's a net in the sense of a net. All right, a net is, you've got a directed index set, yes, and there's a map, an inclusion preserving map from the directed set to whatever, the thing that you're looking at, yes?
for non-algebra, there's no relations, no inclusion.
At that point, no, that's right. At that point, no. I mean, but it's precisely those inclusions which are going to determine whether or not the group J manifests the correct algebraic relations.
It's not an ordered set, it's a partially ordered set.
Yes, the set I is partially ordered, yes. Partially ordered. I thought I said that, but if I didn't, I'm sorry. Partially ordered.
So, but you have characterized so essentially the point is to characterize a partially ordered set, so the partially ordered set which are isomorphic to the set of weights. It's not just
Okay, so that is, in fact, a step beyond, right?
Yeah.
So I agree that that ought to be possible, and I've thought a little bit about what kind of additional structure you could place on that partially ordered set that would entail the algebraic relations among the J's, but that is an extremely difficult problem, and I haven't made much headway with it. But that is, in fact, a point.
I think it was more technical.
Okay.
You put on page 19.
Page 19, okay. It'll take a while to get there. Let's see. Yes.
This group generated by modular involutions.
Yes.
Modular involutions are antilinear. So
That's correct.
What is this group
What do you mean, what is it?
generated by antilinear?
Well, it's
Linear or antilinear?
well, there are, well, the subgroup, there's a subgroup I talked about, which is the products of even numbers, all right? That is,
Generated by products of pairs.
that is a subgroup of this, yes? But you can also, there's nothing,
Modular gives you linear.
yeah, I know, but you can also consider products of odd numbers of J's. That gives you, that's also in this group, yes? So some of the elements of this group are going to be unitary, others are going to be anti-unitary, and others are going to be nothing whatsoever because they don't compute with each other, yeah? Okay.
Okay.